Hello and welcome to this first of the year FDTD Satellite Applications webinar. Dan Baumgart, who is the Sioux from La Crosse, he's been there for 25 years now as the Sioux, is going to be talking on Goes East cloud top signatures of weekly forced snow events. Go to the next slide, please. This is part of an ongoing series of webinars, Forecast Decision Training Division Satellite Chat or GOES Applications webinar. I'm Scott Lindstrom, and Dan Bykos and I are always looking for presenters. So if you know of someone in your office or you yourself want to give a presentation on how you've used satellite data for a particular problem, please let us know and we'll help you get things set up. Next slide, please. There is some protocol. We'll have about 20 minutes for Dan's talk. If you want, you can send questions via GoToChat, or you can ask them afterwards by phone. Don't press hold, and mute when you're not speaking, and we'll be done by not 20Z, but probably 1830Z. Take it away, Dan, and thank you.
All right, thanks, Scott. Yeah, this is some work that I worked on with Patrick Ide, who when we first did it, took the lead on it. He's now the Sioux in Duluth, and Phil Schumacher also in Sioux Falls. And I was talking to Scott last year about bringing it up, but I think it was March when we first talked about presenting this again. And we had presented this, Patrick presented this at the NWA conference in 2018, after we had started seeing some different signatures on the new GOES craft at that time. And so it was a nice research to operations and back to, it was kind of a operations to research to operations kind of a path we took here, where we collaborated with Scott and some other people at Sims to kind of find out what was really kind of going on with some of these signatures that we were seeing across the northern parts of the states in the heart of winter in these Arctic air masses. And so I appreciate you joining in today and spending a few minutes as we just kind of go through some of this work that we brought together. So the title is GOES East Cloud Top Signatures of Weekly Forced Snow Events. And we'll kind of get to a little bit of a kind of a case study and have you kind of think about what you would do in the scenario that with some of the data that you'll see, and really kind of started with just that we were getting some signatures on the cloud top phase, a low stratus in January in the heart of winter in this Arctic air mass that really wasn't making sense for the temperature regime that stratus was in. And so the forecaster, really kind of had to reassess what the conceptual model there was and what their expectations were for snow producing clouds in these Arctic air masses. And the two didn't jive, and we'll talk about that a little bit. Let's just start with a case that kind of got the ball rolling here. I'm just going to show you the sounding for Minneapolis here. Now, this is a pretty cold air mass. We got -10 highlighted. So we've got this somewhat saturated layer. There's not obviously 100% saturation in this deep layer. But you can see that if cloud exists, it's pretty cold. It's colder than -15. The stratus, there was stratus in this sounding, and it was somewhere between -16 and -22 Celsius. So when you look at ice initiation and getting the ice growth process going, this was well into the probabilities where you could initiate ice growth within the cloud. And a little bit further upstream in Aberdeen, a little bit further west, more in what I would say in the heart of just the low level stratus, you can see that the temperatures were fairly similar, -14 to -18 in this regime. And the cloud top was somewhere around -14, I guess, with my red dot. Again, really into the probabilities of this being ice cloud and having snow as the result, right? So we jump into a short loop of the GOES East data at this time. This is just the clean IR channel. And we've highlighted in this the minus 15 Celsius temperature. So anywhere you see that blue coloring starting, it's the clean IR is sensing that the cloud top temperature is at least minus 15 Celsius. And you can see a pretty predictable, what expected, I guess I'd say, response at the surface. You're getting some snow showers. You've got a cyclone that's a little bit further north, over northwest Wisconsin, with a little bit better deformation going on over northern Wisconsin into the northeast Minnesota with more widespread snows. And then this low-level Arctic stratus layer that's warmer, but still, minus 15. So really the sounding temperatures and the IR imagery really go together well. And my question would be to you, if you went and looked at a GOES cloud top phase image for this low-level stratus, what would you expect to see? Or maybe some of the other channels like the snow, the cloud channel, the 1.61 snow ice channel. What would you expect to see in looking at the data set and the data that we've looked at so far? And so here's one of the big reveals here here's that low-level stratus stack, and we're in the daytime, so we can get a good sampling of the snow ice band here, the 1.61. And again, a reminder that the lighter colors are liquid and the darker colors are the ice. So you see definitely to the north of the circulation here in the deformation area, you've got deeper, colder cloud and ice top clouds. But in this entire stratus layer, you've got what the satellite is sensing as super cooled liquid. And that maybe doesn't fit a conceptual model that you had in your mind for this air mass, especially with snow being the outcome at the surface. So what about the cloud top phase product? Here's the same loop with cloud top phase in that bright greenish color. At least that's the way my eyes see it, and I'm colorblind, so it may be more yellow. But it's super cool, there as well. And then as you move off to the northeast, as you'd expect, you see the ice there. But really, we're talking about super cool liquid cloud tops through this whole area. And so that really was kind of the impetus to bring this to SIMS and say, hey, what do you think is going on here? Are we missing something in our conceptual models? Is the satellite sensing something that we, aren't used to? Basically, it's an inconsistency maybe on what you'd expect between what the thermal profile is giving you, the snow observations at the surface, and the cloud top phase. So then I think Jordan Girth dug up this paper to kind of get the ball rolling and some of the conversation going. And this is some research actually from a field study. And man, I don't know if you know me, but I'm kind of a cloud physics guy. So I like, cloud physics. And to me, the field studies papers are some of the most fascinating papers where they're doing actual measurements of what's in the clouds. And so this one was from, I believe it was called the mixed phase, it was MPACE, the mixed phase Arctic cloud experiment, where they had some field sensors. And so we're going to look a little bit at that. On the left-hand side, that's what you're seeing there. It's basically a vertically oriented cloud radar, and then a LiDAR also at the same spot, giving us an idea of what's in the cloud. And so what they found was that in Arctic air masses, the cloud top is as many of you know that forecast, the cloud top strongly associated with the inversion top, and in that area, your vertical motion is typically decreasing, right, on the cloud top itself. And so therefore, the vertical motion max is really found below the cloud top. And at cloud top, there's higher probabilities of water content. And so this is just one of their cases that they sampled. I've got time along the bottom of axis here. The x-axis is just time, where they were sampling looking vertically at the stratus that was moving over. the top, kind of typical of the last case we looked at. Maybe you'd have a sensor in southern Minnesota looking at the clouds as they rotated around the low in this stratus area. And so you can see on the top of this that the phase here of the warmer colors are liquid or mixed phase. And as you go towards the very top of the cloud, and this is just kilometers on the left-hand side, so it's a cloud that's about 1 kilometer above the surface as cloud top, you can see that the reds and oranges actually increase at the very top of the cloud. And so what they were sampling is liquid at the very top of these clouds. And then as you move vertically toward the surface, you see it becomes dominated with snow and ice. And then so this is just the phase. If we look at just the ice water content and overlay these black outlines here of kind of the transition zones in the top of the cloud, you can see that the ice water content is from about halfway into that mixed layer and vertically falling towards the surface. So these are just kind of snow showers or flurries passing by the sensor. And so if they isolated the liquid content, you can see the liquid content here at the top portion of the cloud, but also the highest liquid content, these reds, are right on the very top of the cloud. And so, you know, that what we're seeing here is that the vertical motion is really anchored below the cloud top, and the vertical motion is decreasing as you hit the inversion layer. And so your vertical motion is making your saturation more preferred. You have super saturation over ice at lower portions of the cloud. And so therefore you get ice nucleation below the cloud top. And the cloud top, where you're you know, theoretically not seeing the saturation as much because the vertical motion is dropping off, you tend to be dominated by just super cooled liquid droplets, or possibly maybe drizzle droplets if they grow a little bit. But for the most part, it's a stable liquid layer right on the top. And so, you know, this whole process is in the vertical motion max, again, below the cloud top. Ice growth is initiated and sustains itself, and then the ice obviously falls toward the surface and gives you snow. And so Shupp gave this conceptual model in his paper, and there's kind of a lot to unpack here, but here's his picture of these enhanced vertical motion areas, if you will. And the black shading here is liquid water droplets. And so if you were the satellite looking down on this event, you know, or this conceptual model, you're going to have a liquid water layer really across the whole top portion of the cloud in these Arctic mixed phase cloud situations. And vertical motion will vary within that cloud. And you can see his representation of the ice saturation and ice growth process taking place in the vertical motion max a little bit below the cloud top. And so he's got a depiction of the relative humidity. So if he drew a vertical line here, on the left-hand side, you see height, so 1.2 kilometers. His idea, his conceptual model is that in the updraft, your liquid relative humidity is at 100, and then you're super saturated with respect to ice. And so that's where your ice content and ice growth occurs. And so you see this dashed line, basically a non-zero ice water content. And your liquid water content is maxed at the cloud top and then drops off as your ice water content kind of kicks in below it. And then you have flurries or light snow at the surface. So the downdraft is you know, kind of a weaker version of the left-hand side where your saturation is more limited. Your liquid saturation is not there, and your liquid content just kind of sits there without much ice water content because of the vertical motion, the lack of vertical motion, so you're not generating those ice crystals. So that is seen, if you come back to the case that we looked at here, that's seen as, you know, these areas, you know, you have these flurries move through and then it stops flurrying and you're just left with cloud, and the entire cloud deck is capped by super cooled liquid water. But below that, you got that's where you got the excitement going on to initiate the ice growth process. But then it kind of explains too these areas of updraft and downdraft of why you see flurries or why you have flurries that are kind of intermittent when you're in one of these air masses. So just another part of that experiment, another day of sampling in 2004 near Barrow, Alaska. And here's a cloud. They sampled from 500 meters to about 1,300 meters. Two different devices here, one looking at ice crystals looking at this gives you an idea on the size of the ice crystals. And on the left-hand side, you're looking more at the cloud droplet space. And so this is 200 microns. So we're looking at cloud droplets here at 1,300 meters, kind of transitioning as you go vertically to see some of these ice initiation or rimed ice growth kind of at the bottom here. And then these are all ice particles and where they're showing up within this cloud layer. And then on the right-hand side is just the temperature profile. So you're -10, decreasing temperature, and then bang, you have this inversion. And so your cloud top is kind of in this area here. And on the far right, they're showing the water content of the cloud, and you can see that max is kind of right at the cloud top, right at the inversion height there. And it never fails. I swear to God, every time I give a webinar, the phone rings, and our phone never rings. That's hilarious. So the streak continues. So here's the cloud top, and these all three match horizontally. And so you can see the liquid dominance at the top of this cloud here. And then some of the ice initiation going on further down below, and then the ice crystal sampling from these microphysical samples that are done here for this experiment. So again, that kind of replicates what Shup showed in some of our other work. And so kind of boiling it down, this is how you'd have that fall out with a liquid cloud top, mixed phase area, and then mostly a rimed ice or ice crystals falling to the surface as flurries. So there's a couple other cases I just included. Here's just a cyclone that's moving through North Dakota here. This is from Patrick, had this case when he was at Bismarck. And you can see that really nice cyclone here, and the temperature regime, again, we colored the -15 blue. So it's not that you can't use your IR imagery, it still gives you some sense of what that low-level cloud top, that low-level stratus cloud top temperature is. You know, we're still looking at very cold cloud, and you can still expect the ice nucleation to occur within that layer, provided it doesn't really warm up below that layer or that level of sampling. But again, here you see the similar case here where you've got supercooled liquid cloud for most of the cloud here, and you see this area in northwest North Dakota. It's snowing at the surface, 7 degrees, 9 degrees, 10 degrees. The IR imagery again, -15 at cloud top for this layer, but the snow ice band giving you liquid. Also over south central, more near Bismarck area here, again, super cooled liquid. So I guess the bottom line is don't let the super cooled phase throw you off from a forecast of flurries and snow when the thermodynamics say it's right. Here's another case in Nebraska, and just a little bit more vigorous cloud band here, where the snow ice channel in that cloud band, if you look at point F here, it's located right here, and then the snow band extends to the southeast. This entire band is sensed as mainly liquid in that band there. And here we're talking about a little bit warmer cloud here, but even then below it, we're getting snowfall at the surface. So it's a little bit warmer situation, not the 7 and 10 degrees, but again, the ice process occurring below the cloud top. So in summary, you know, it just kind of made us kind of come full circle. So this presentation is more like an awareness of trying to spread some of that that knowledge gained to refine our conceptual models and think about you know, the science of it, but allowing that cloud that some of these Arctic clouds have a stratification within them, and that the top may be super cooled. So don't let that throw you as a forecaster that in these air masses, if you see super cooled phase in the snow and ice channel, or in the cloud top phase derived product, that that you're going to get a liquid outcome at the surface, that they can still produce the snow. It's just going to be a mixed phase cloud, and the snow would fall, obviously, or be generated in the ice region below the cloud top. Are there possible aircraft icing implications? There could be. It's a very shallow layer that a plane would have to fly directly in for an extended period of time, vertically, if they would elevate or go below that liquid cloud layer. I think they would be okay for icing, but there is definitely a super cool layer in there at cloud top. So again, this is just a nice example of as forecasters observing something and taking it to a research group and reaching out for those, if there's SUs on the call, if there's, reach out to a group that is more knowledgeable in this area and bring these operational examples to them. And it's a great circular loop that you can do. And then you can bring something like this back to the forecasters or operational forecasters in the Weather Service and share that. There is also a blog on it that was done some time back. And just in closing, I wanted to thank some of those people that we worked with, Jordan Girth, Scott Bachmeyer, and then Scott Lindstrom, who's on the call today. But again, a nice O to R to O circle or path that we took with this work. And that concludes my talk today, and I can again entertain questions that may be out there. And I again appreciate, I know you make choices during your day with your time, and so I do appreciate you joining in today.
Thanks, Dan. Always interesting. I'll just make the comment that because you don't have the ice, that's really going to change. You showed a picture of the day cloud phase distinction. I know that's a popular RGB. And when you don't have the ice, the day cloud phase distinction, it really shows up in that. So if you use the day cloud phase distinction for any kind of way of saying, okay, this is where the ice is, keep this particular topic in mind if you have shallow, very shallow cold air. Does anyone have any comments? I don't see any hands up. Dan B, can you unmute everyone so they can just
Sure.
Mic goes. Too
Yeah,
many Dan.
I think you have the power to do that. Dan, do you have the power to do that? Or
yes,
is it me?
I just unmuted everybody.
All right.
So if anyone has a question, just take the bull by the horns and start asking.
Hi, this is Carl Jones at NWS Grand Forks. I have a question. Have you made any comparisons to these cloud top signatures to cases where it's been actual freezing liquid making it to the surface? And is there a difference that maybe we can latch on in our conceptual model to distinguish between maybe this snow in a warm cloud type of situation compared to when it actually is like freezing drizzle in a warm cloud signature?
Yeah, I haven't. I think what you said there though was the key is that you're focusing more on the warm cloud signature. This one, this color regime here on this example is not down to -15. So it's a little bit different on this image compared to the last one that we showed. So, these temperatures are colder than they appear in this picture. But I think, Carl, the idea is that your cloud and your IR temperatures and your thermodynamics are warmer, which obviously lead you out of the spectrum and the probabilities of getting ice nucleation. I think that's the key, is that you have to nucleate ice in these situations. And there may be, there's probably some middle road in there where you're on the fence with it. That once you're in that -8 cloud top or layer temperature regime, your probabilities are going to say you're going to be struggling for the ice to be created. So use the IR temperature to help you with those diagnoses where the cloud top phase is liquid for both of these, both the liquid outcome and the flurry outcome or light snow outcome. I would say use the IR imagery, but I haven't done that exactly, but that would at least be the application in my mind.
Great, thank you.
Are there any other questions?
Scott, I see there's a question from Jack. Do you want to read that off in the question chat box?
Okay, let me. The question was, how much snow actually fell in these situations?
That one is, I can't remember. The first two were kind of a flurry situation. Just light snow for these. I think it was not a big deal. This one I'm not sure about. This was Phil's case, and I don't recall if that was a transient band or if it stayed put a little bit more. So I can't give you the answer on that one.
So more likely nuisance versus like plowable.
Probably, yeah, for those first two at least, right?
I had a professor who categorized snow as nuisance, plowable, and crippling, and I find that useful.
Yeah.
Are there any other questions? I don't see questions or, okay. If not, we'll end a little early and give you some time back. I greatly appreciate, Dan, your giving up your time today to give this presentation. Check your emails for a future FDTD satellite applications webinar. And as always, if you have ideas for presentations, send off an email to either to me or to Dan Bykos. We both have NOAA.gov accounts. And that's all we have today. Thank you.